Having easier processes really will drive toward to a more sustainable utilization of resources. This is particularly pressing now where we understand that feedstocks are limited. That's not only fossil fuels, that's really all our feedstocks. Especially with growing populations all over the planet, we have less and less feedstocks available, so we have to use them more and more efficiently. And that requires as little waste as possible, as high efficiency and transformations as possible, as little steps in making complex molecules, and the key part to make this is catalysis. And I'm not specifying what type of catalysis, but really we need enablers for this type of chemistry. So it's, on an academic level, it will be essential to discover new reactions, to have new concepts of how we can generate complex molecules. So that are, go ahead.
I've heard catalysis influence the rate of the reaction. Do they also influence the efficiency?
We come to that in a second, yes. So what is so I will talk, this is the outline. I'll come to this in a second, so I don't want to ignore it, but I have actually a slide on this, so we'll just fast forward. So what I thought I will cover in the next hours is, well, first to give you a bit of an introduction, so exactly to your question, what is catalysis, what are the fundamentals, what are the aspects we have to consider. Then we look at different activations, especially those that are relevant for fossil fuel feedstocks for energy-related transformations. Dihydrogen bond activation, carbon-hydrogen bond activation, and we split this a bit in 3 different subsections. First, very reactive CH bonds, where we learn a lot of concepts and principles. Then aromatic ones, which are very useful for synthesis. And then, in the end, we look at very unreactive CH bonds, like from alkanes. How can we make alkanes feasible for our chemistry? And then, in the end, or that's at the moment scheduled for the end, I'd like to tell you a bit more about heterocyclic carbenes as a unique platform. I would consider that phosphines have been in the world for 30, 40, 50, 60 years. Most people know plenty about phosphines, like conanyls and so on. Carbenes may be a bit less common. Many of you, and I know everybody who has at least seen G10's lab, he should dream about carbenes, so they all know it, but then others may not so know. And we can extend, so we can skip here if you think, well, some of this you already know and you have covered already many times. We can skip, we can as well expand. We can also move much more into the domain of carbene chemistry, carbene catalysis, or not. So this is a bit of an interactive system. If you're interested in highlighting specific topics, let me know, and we can dwell a bit more on it. Because I've never done such a course, I thought I start with, what would I expect you to know a bit? If there are things you don't know, let me know, and we can quickly introduce them so that you're not, not that I start talking about things and you have no clue what it is. But I hope that you know a bit what hard-soft acid-base concepts are in coordination chemistry, which ligands prefer what metals, why is this so, or what metal oxidation states, what are the underlying factors there. You'd know when you see a reaction, whether it's a redox reaction or a substitution, really the 2 basic fundamental reactivities that we have in chemistry. So that you know the basics of organometallic chemistry, that you know whether reductive elimination is an oxidative addition, beta hydrogen elimination, a migratory insertion, and then the substitution, of course, is you have it. That you'd be able to count electrons at the metal, how many valence electrons with the ligands, how much, what is that? So then this, you understand what the ligand is, that kind of puts together, and then that you know a bit what is a sigma bond and the pi bond, what is pi back bonding, what is the requirement at the metal, at the ligand to have pi interactions, be this pi donation or pi back bonding. So that will be a bit of, if you know this, I think you're ready to follow. If this is trivial, and that's why the whole hydrogenation, for example, is trivial, let me know, and we better have a coffee or a tea or a beer.
Could you include the first point in the discussion briefly?
Say, the phosphines?
No, the hard soft acid base principle.
Yes, the hard soft acid base. You don't know. Well, who knows about the hard soft acid base principle? Who does not know? So maybe I tell you in a break. Is that okay? Rather than if everybody knows, everybody will go for it. So, catalysis. What does catalysis do? So principally, the very strong, the early definition goes back like almost 200 years. So a catalyst is a substance that increases the rate of a chemical reaction and is not being consumed. So that's a very fundamental concept of catalysis. Note that in here, it does not principally say that we have to have like a recycling of that substance. So, for example, classic esterifications you do with 2 or 3 equivalents of sulfuric acid. You take an alcohol and acid, you add like 3 equivalents of sulfuric acid, you get the ester formed. This is a proton catalyzed reaction because the acid and the alcohol spontaneously don't react, at least not at ambient conditions, but we use a proton for each molecule we produce. Now, of course, that's not so sustainable. Ideally, the catalyst takes a substrate, transforms it to the product, goes and takes another substrate, and does this many times. But so the key definition of this one here is that principally the thermodynamics of a reaction are not affected. The stability of the product, the stability of the starting materials are not influenced by the catalyst. What is influenced is the activity, the barrier that the reaction has to cross to let the reaction go. And that's healthy. Otherwise, if there's no barrier, you know, the wooden chairs you're sitting on, they would all be carbon dioxide. So there's an activation barrier, that's good. During a catalytic reaction, the catalyst does undergo a series of transformations, typically. So it is changing, but it is released at the end into its own original form. So it's not that it's just sitting there, it gets transformed, but eventually it's released as it has been entering. So we have to consider 2 types of things, additives and catalysts. An additive has a different function than a catalyst and has different consequences. I tried to put this together in a drawing because I'm not so versatile with my computer drawing, so I put it with an old-fashioned pencil thingy. So this is kind of an energy platform of what we're having, say, a substrate that has a certain energy, and then, so that's an energy surface, if you like, and then you have a lower surface here that is the energy of the product. So whether we have the reaction catalyzed or non-catalyzed doesn't change anything at these ground energies. In a non-catalyzed reaction, the reaction may go very, very high. So we need a huge activation energy. In a catalyzed reaction, the catalyst starts to interact with the substrate, maybe early, maybe late, and undergoes a couple of transformations to eventually form the product. Now, the highest activation energy in the catalyzed process is significantly lower than the highest activation energy in the uncatalyzed process. This system fulfills the Berzelius conditions, and the reaction, the catalyzed reaction, will be faster than the uncatalyzed. With an additive, we start, in contrast to a catalyst, we start to form an encounter system, like an adduct, which is here considered as this SB adduct, which then is carried through, but may not activate the catalyst. It may stabilize early intermediate or late intermediate. And with an additive, it depends whether then the stabilization of the ground state here is larger or smaller than the stabilization of the highest energy transition state. So some additives can be inhibiting because they don't lower the transition state too much but stabilize the intermediate. So then the actual barrier becomes larger than the uncatalyzed process. So additives can have a dual effect. So it's important to see, so the delta, again, so the ground states are all the same, but the catalyzed and the uncatalyzed and the additive activation energy can be different. So this is a general condition, the delta G activation of the additive can be anywhere. This is, put this here arbitrarily, it shouldn't probably have it. So we can, principally, we can show the whole system as a cycle. We have a catalyst that somehow enters a so-called catalytic cycle, where it grabs a substrate, it forms a catalyst-substrate complex, it starts to transform the substrate into an intermediate. The intermediate gets further transformed into a product. The product is released from the catalytic cycle, and we reform the catalyst. Now there's a few important notions and definitions down here. One is that typically what we put into a reaction mixture is not the catalyst but the precursor. Typically the complex or the system that we put in a solution needs to get activated. It needs to lose a ligand, it needs to start to get oxidized, it needs to make a solvate complex, whatever. There's some sort of activation that then forms as well a deactivation. And we can have this anywhere on the cycle, activations and reactivations. And we can, if this is reversible, we typically would call it an activation or a deactivation mode. So if a catalyst is deactivated, it can be reactivated. But then the catalyst can also decompose. That is, it does a side reaction that is totally non-productive, but it transforms the catalyst. So now the catalyst irreversibly goes off the cycle and can't get back to the onto the cycle, and so it's lost. That's one thing. The other thing is that once the catalyst is in its active state, typically the barriers are all very low, and it's very difficult to start looking at what is the catalytic active species, because it's reactive. So whatever accumulates is likely nothing on the catalytic cycle. Now there are exemptions, but I'd say in 95–99% of the cases, if you follow a catalytic reaction and you see a species that is built up, it's most of the time something here, or something here. It's something that's out of the cycle, it has a low energy, and it has a low energy because it's not in this wobbly line that does the transformations. So that has direct implications in how we look at catalytic reactions and how we interpret our observations. Typically, what we see is not a thing on the cycle, but it may be very close to the cycle, and the more we understand of what are the dormant species, the more we actually see what could happen. Because everything, if everything is close enough to the cycle, we can start to build up such a thing. So, that may tell you a bit of, so there's many, so principally, if the catalyst does one cycle, it is a catalyst. It has to be backed formed to what we originally had. Now we will see reactions where this cannot be shown, because this system here is so hot that immediately it reacts further. So we never see the recycling of the catalyst because it's too reactive. So it just transforms till there's no substrate, then it burns, then it's gone. So the question, of course, then is, once we know what a catalyst is, we need to know what is a good catalyst. So we could have a catalytic species, say a catalyst A, and we have a catalyst B, and we let them work for 20 minutes. This one gives 60% conversion, this one gives 80% conversion. Can we say which catalyst is a good one and which one is better? B is better. Why? Why is B better? So what makes a good catalyst? When is a catalyst good?
for the same amount of catalyst use if the rate increase more.
Yeah, let's say we both use 1 mole percent, huh? Same concentration. So that's the conversion at 20 minutes. So what are the criteria that make a good catalyst? High
turnover.
High turnover. High turnover.
Low activation energy.
Yes. And if we have lower activation energy, what is the consequence? The rate. So that's the same as high rate. Yeah?
What selectivity?
Selectivity. High selectivity. So what do we know here? What is the turnover number? Can we say here something about turnover numbers out of this one? Can we say something about the rate? Or can we say something about the selectivity?
The rate is higher for this.
The rate is higher. You agree? The rate is higher? No? I'll show you two reaction profiles. This is the time. There's my 20 minutes. I put the 20 minutes here. There's my conversion. Okay? So the thing that I know is that one catalyst goes at 60 and the other goes at 80. So there are two possible reaction profiles that lead to exactly that point. Now we know the rate is not higher. Huh? So now here the rate is actually superb, while here it's only low. It could be the other way around. And then we get the 60 and the 80 and yes, now you're right. So we can't really say. It could be this one or the other. And we can't even say something about the turnover numbers. We can say something about the turnover numbers at these 20 minutes. But because that's a single thing, we can as well think of it. I don't know, in the end, this one goes to completion, this one somehow gets stuck and it's dead at 80%. And because these are conversions, what do we know about selectivity? Nothing. We just know conversion is typically the consumption of product. So in order to start characterizing a catalyst, we need much more than single data points. So what can be helpful is either that's a sign to break, or that's the fire alarm, or that's no.
This is the usual class time.
Okay. 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 So we ignore it for a moment, unless it goes on for 15 minutes and you can't hear me anymore.
It will be for 30 seconds.
Okay. 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 So we need to define those things. And then we can start thinking of what is a good catalyst, what is a bad catalyst, and how can we characterize it. And so the turnover numbers, I put them on here. So the turnover numbers are, there's a clear-cut definition. How many substrates are converted per catalyst. And that for this we need to know the concentration, so the catalyst concentration typically in mole percent per substrate, and then we need to know the conversion, and then we can decide. So if this is 1 mole percent, these are 1680 turnovers. The turnovers tell us, high turnovers tell us that the catalytic cycle is very robust, so that we have very little of this one here. The turnover frequency tells us a bit more about the efficiency, how quick. So one is how many times the cycle goes around, and the other one is how quick the cycle is going around. So this is like cars, if you like. So a Toyota runs forever and ever and ever. If you have a Ferrari, maybe if you don't oil it properly, it doesn't. But then for the turnover frequency, your Toyota is not that great compared to the Ferrari. So you decide which kind of one. So turnover frequencies we have, and then for the turnover frequency, I should add, it's very important at what stage you measure the turnover frequency. And there as well, when you look into the literature, you see all types of bogus. So you'd see that the turnover frequency basically is the slope of my conversion curve. But in a classic reaction, the slope changes because at some point you have substrate limitation. The more you convert, the less substrate is there, so your rate changes, because your rate is typically dependent on the substrate concentration. So at the beginning, you usually have a seed of 0 order in substrate, because the substrate is in vast excess, especially if you have low catalyst load. So typically this is close to a straight line. So what people sometimes refer to is a turnover at initial rates. So the initial turnover. Now that can be a bit dangerous, because it depends then where do you define initial. But it's a very good initial approximation. Also, another difficulty arises if the system has a bit of an activation, an induction time. So then there's a lag time, then the whole thing, gets slightly sigmoidal, because the catalyst needs to get activated, and this is not because it's a homogeneous solution, this is Gaussian distributed, so not all catalyst enters at time X, the active stage. So you get at the beginning little conversion, and then the catalyst reaches its full potential. So there you can have the TOF max. So you take where is the catalyst in fullest swing, where is the slope the steepest. And then another version, so that's the last one, is to look at the given conversion. So you measure the reaction at 25 or 50% conversion, and you look how fast is it then. That allows you to compare. So the TOF ini would be like you define a time, or you generate a TOF 10 or TOF 25 or TOF 50, and you decided what conversion do I take, do I compare. This should be early, it should not be more than 50, because the more you go, the higher you go, the more you reach, you leave the pseudo first order, pseudo 0 order conditions in substrate, and so the more this number starts to vary. And then the TOF max, of course, is removing that issue of induction periods, activation, catalyst activation. So the TOF reports are not always unambiguous. It's always good to specify, and for sure to take the TOF at some given time and not endpoints. And the classic issue, maybe if I take a hypothetical reaction that runs for 4 hours, Then I have at 3 hours, I have already 100% conversion. So the TOF would change if I measure after 3 or 4 hours if I take the end point. And that's ridiculous. The TOF determines the capacity of a catalyst. So the catalyst doesn't change if it stays an hour longer in a reaction solution. So it's very important to take this somewhere, either time-wise early or conversion-wise very early. Then the selectivity, that's the last bit. So the selectivity is defined as, how would you define selectivity of a catalytic reaction?
Moles of desired product upon total moles of product.
Moles percent of?
Desired product upon total moles of product.
Okay. Yeah. So that's basically the total product is identical to conversion. So this is, sorry, this is the yield, not. And you see they're both. Traditionally, we report conversions for a catalytic reaction. Ideally, this is the same as yield, then we have a highly selective reaction. This is for reductions, this is often identical, but then oxidations are more tricky, especially because in oxidations, if we have partial oxidations, over-oxidation is an issue. So then the yields and conversions are not the same really anymore. So it's important to specify and to not just look at the disappearance of a product of a substrate, but also to the appearance of the product. Then we get this all together. Good. Then I should spend a few minutes if we talk about catalysis. I think we specified a bit, but I'm not sure, because in my mindset always when I talk about catalysis, I talk about homogeneous catalysis. But of course, the catalysis field is much broader, and if you open a journal that is called Catalysis, then you see that a huge portion is actually heterogeneous. So that's a massive area of research, very productive, very important. So we should look at, and there's a third domain of catalysis that is equally important, and that will be the enzymatic catalysis, so biocatalysis. And they all three have their own pros and cons. I put here down together all the the characterizations of a heterogeneous and of a homogeneous catalysis reaction. So key is in a heterogeneous reaction, the catalyst and the substrate are typically in different phases. And most commonly the catalyst is a solid and the substrate is either a gas or a liquid. So steam reforming will be a classic, ammonia formation, and so on. While in homogeneous catalysis, the whole system is homogeneous, so always in the same phase. So enzymatic catalysis is typically homogeneous because everything is in water, everything is properly dissolved. So heterogeneous catalysis is of course benefiting from very easy product separation because we have different phases, so it's very easy to join this. The catalyst system is typically extremely robust, so it's easy to regenerate the catalyst, and we have a huge variety of conditions that we can apply. And huge is really huge, you know, thousands of degrees centigrade. That's even warmer than the summer day here. Typically, costs are extremely low of heterogeneous systems because we talk about surfaces. These surfaces contain very little organic material, almost no ligands. There may be blends, there may be doping, but that's it. So the costs of making the catalyst, of using the catalyst, are fairly low. And so we can use high throughput. We can go with large quantities on those catalysts. There's a few drawbacks. One is that typically the rate is very low, the selectivity is very low, and the understanding of what's happening is extremely unpredictable. So we have very little knowledge, we have very little ideas even of where catalysis is happening. So if you think about the surface, a surface is typically a super ill-defined construction. So a surface may look like and we don't know whether it's these holes, whether it's these exposed areas, whether it's these kinks that play a role that are catalytically active or not. Because clearly here you have like 10 different sites of the same metal, of the same surface, but 10 different activities. This one is different from this one, is different from this one, is different from those ones, these ones are different. So we have everywhere a bit different activity at the metal surface, and that makes the reproducibility difficult. So classic heterogeneous catalysis suffers from batch to batch reproducibility. And I don't know whether you have done any hydrogenations with palladium on carbon or ruthenium on carbon. Typically an organic lab would have a drawer where the hot palladium on carbon is. And then there's everything that's on the shelves are the palladium on carbons that are inactive. So, you know, some of the poor students, they take the first step saying the reaction doesn't work out now because the hot one is killed. So this is a classic problem of activity. Homogeneous catalysis has there some advantages. The catalytic active species is typically extremely well defined. It's in a very specified pocket where the metal is residing, and this allows to tune selectivity. The reproducibility is very high, but then there's some of the drawbacks that we have here. There, or the benefits that we have from the heterogeneous systems are negatives in the homogeneous case. Difficult separations are a key problem. So we have often it's tedious to separate the catalyst from the product stream. People have tried many things, immobilizations, this, that, and the other. Turns out that none of these immobilization strategies really work for industry. So, there's many ingenious ways on polymers, on dendrimers, on solid supports to attach your homogeneous catalyst. Typically, this doesn't work. And I know from some colleagues at industry, they try to reproduce it, they have problems in the lead chain, so they lose the heterogeneous aspect of the immobilized system. The activity goes down, so all in all, at the end, you have, it seems that if you do immobilization, you have all the negative impacts of the heterogeneous system combined with all the negative impacts of the homogeneous system. So really, it's a lose-lose situation. So that seems not so productive. Typically, homogeneous systems are very sensitive, so we have to be careful. Oxygen may be an issue, but also other ligands that can coordinate. And we may have side reactions because the catalyst is really active. Now in enzymatic chemistry we have even a different type of activity. Typically the catalyst is extremely selective, extreme, for one substrate only. And you add a methyl group to the substrate, the catalyst doesn't work. But because of this super high selectivity, the system evolved to an amazing activity. So turnover frequencies of enzymatic reactions are skyrocketing. So this is unrivaled by the low rates in heterogeneous system anyway, but even homogeneous systems. There's rarely a homogeneous system, or I don't know about a homogeneous system that would be only close to rates that we see in enzymatic reactions. They're just extremely fast. And product separation is a bit easier because we can now use like centrifugations and so, because the enzyme is such a massive thing. But then, of course, the disadvantage of enzymatic catalysis is that first turnover numbers are a problem, because we have only, if we have such a huge colossal enzyme that runs a reaction, we cannot run huge batch reactions for most of the enzymes. So there's maybe 10 or 20 enzymes that are used industrially. So all the others are academic transformations. And then the other thing that is often a problem is that once the enzyme is specified for one given substrate, one given product, so say if you'd like to have the R alcohol, the enzyme may be superb, but if for whatever reason you need the S alcohol of the same transformation, the enzyme won't work. Very discriminating, and it's very hard to take, say, the other isomer. Hey, how do we know whether we have a heterogeneous or a homogeneous reaction? Well, the most easy, or the easiest way is that we know what we add into our flask.
Can we just go for a break because the tea?
Oh yes, before it's getting cold. Okay. Yes, yes. Thank you.
So we'll just have a break, otherwise tea will get cold.
Ah yes, yes. Thank you for. Yes, we do. Perfect.
The tea is there, I guess. Yes.
This morning.